We now continue with chapter 8, inner product spaces, and the first section is 8.1, inner product. We will have vector space, mostly finite dimensional, unless otherwise noted, and the field of scalars, the scalar field, will be either the set of complex numbers or the set of real numbers. So let's dive right into the definition of inner product. An inner product on V is a scalar valued function, usually denoted by brackets, and the dot means that you have two arguments separated by comma. So a scalar valued means that the value will be a scalar, and since it has two arguments, these two arguments will be from the vector space. So that means that the mapping is from the cross product of the V vector space with the V vector space, and it has to satisfy the following properties. First one, if you add together two vectors, and that's what you plug into the first argument of the scalar product, then we can separate this inner product into two inner products using the first argument. And the second property is that if you multiply in the first argument a vector with a scalar, that scalar can be factored out from the inner product. So that makes sense because you have scalar as a result of the inner product, and that's multiplied by a scalar. So this is scalar. So this should hold for all u, v, and w vectors from the vector space, and for all c scalar from the scalar field. Note that what this really means is that we have linearity. This is a linear function or linear mapping in the first argument. That's not all the properties. A third property is that if we talk about complex field, if we change the order of the arguments in the inner product, then we obtain a complex conjugate of the original inner product. So this should hold for all UV vectors. And this kind of thing, when you change the order and you don't get the same thing, you get the complex conjugate. This is called the skew symmetric property. For example, there are matrices that have this property that you transpose them, which is like switching them around, and you get a complex conjugate of the original matrix. And the first three properties together, where it says that you have linearity in the first argument and you have complex conjugate property when you switch things around, this results in the property that if you try to do the similar things in the second argument, for example, v plus w, you can separate this into two inner products by separating the second components or second arguments. And if you multiply in the second component with a scalar, that factors out as a conjugate of the original scalar. So this is easy to see. You can check using the properties. So this one is called, this property, anti-linear in the second argument, or sometimes it's called conjugate linear in the second argument. And again, together, these three properties and the fact that you have linear in first argument and anti-linear or conjugate linear in the second argument. So that kind of function or mapping that results in scalar values is called sesquilinear. Let me also mention that it would be called bilinear if it would be linear on both arguments. So this is not bilinear, which would be linear in both arguments. So this is just a little bit playing with the definition. And these color notes are just additional notes to the definition, which is not even finished. There is a fourth property that is required for the definition of any product. If you scalar multiply a vector by itself, that will be positive for all vector not equal to 0. So the first example that you should have seen already in undergraduate courses is the so-called dot product. So this would be usually on Rn, where we don't work with complex numbers, or in general it could be on any scalar field of dimension n, where we have x vector, which is just n scalars collected together. Then we can define the inner product of x with y, which is the sum of the ith components multiplied with the of x multiplied with the ith component of y complex conjugate, where I goes from 1 to n. So this is called the standard inner product. It's also called the dot product, or it's also called the scalar product. So we start with vectors and the result is a number. That's why it's called a scalar, because the result is a scalar. And we also have, for this kind of vectors, the standard vectors, we have the notation with the dot, hence the name dot product. So a specific example would be, for example, if x is 3, 4, 1 vector, so we are in Rn, R3, and this is -1, 2, 5, then the dot product will be 3 times -1, the 1 components multiplied together, plus 4 times 2 plus 1 times 5, so -3 plus 8 plus 5, we get 10. But note that we can do this also with complex numbers. We could have 3 plus I, 2 minus I as a vector for x, and for y vector it could be 1 plus I, 3 minus 2i, and I. And then the dot product, in this case it's important that we have to take the conjugate of the second argument. So that would be 3 plus I multiplied together with 1 minus I, the conjugate of the one entry in the y vector, plus 2 times the conjugate of 3 minus 2i, that will be 3 plus 2i, and plus minus I times the conjugate of I, which is minus I. So this would result, multiplying this out, we would get 3, 1i minus 3i minus 2i, then I minus I, it's plus 1, plus 6, plus 4i, and minus 1. So altogether, this is 3, 4, 10, minus 1, 9, and minus 2i plus 4i, that's plus 2i. So the result in this case is a complex number, because we are in the complex scalar field. In the next example, let's consider matrices, n by n matrices. That is actually invertible and symmetric, and the vector space will be n vectors in this from this scalar field. Then one way to define a scalar product or a dot product or an inner product, if these are column vectors, which is usual for vectors, is to have U transpose A V conjugate. So there are different definitions of this. I'm using a little bit different one than what the book does. The nice thing about this is that you don't have to multiply together two matrices in addition, but what we need is a symmetric invertible matrix for A. And if you check what the result is, so we have a n by n matrix here, multiplying n by 1 vector, and this is a transpose, so this is a 1 by n vector. Then all the dimensions line up, and the final result is 1 by 1 vector, which is a scalar. And you can also check that because of this conjugate in the second argument, it will be antilinear in the second component and still linear in the first component. Also note that if we choose A equals to I, special case, you can check that for the identity matrix, or n by n identity matrix, it is symmetric, and also it's invertible. Its inverse is actually its own matrix. And what we have in this case is a U inner product with V is a U transpose multiplying with identity and V conjugate is actually just the U transpose multiplying the conjugate of V, which is exactly the definition that we used. The UI component multiplying the VI component's conjugate and adding this up from I equals to 1 to I equals to n, which is the standard inner product. Inner products are also important in infinite dimension, extremely important, I would say. If you consider the continuous function over the interval 0, 1, if you have f and g from this space, two functions, then we can define the inner product of the two functions as the integral from 0 to 1 f of t times g of t dt. If you check properties, all these properties come from the integrals properties. The third one is actually now says symmetric because we are talking about real valued functions. So property 1 and 2 comes from the linearity of the integral. The third one actually says that fg inner product is gf inner product because we have real valued functions. So the complex conjugate doesn't do anything for these numbers. And the fourth one says that when you take the inner product of a function by itself, you get the square multiplying the function by itself. You are integrating the square. And what we have is from basic calculus 2 or end of calculus 1 is that this is a non-negative function when you square the values of real numbers. So that means that this is greater than or equal to 0 and equals to 0 only if f is identically 0 on the 0, 1 interval. Let me mention that there are also so-called weighted inner products. Here, if the vector field is the space of continuous functions, but not from 0 to 1, but from minus infinity to infinity, which is also many times denoted as the continuous functions over the whole real line. If w is a function of this vector space, then we can define inner product. Sometimes the weight is placed as a subscript as the integral from minus infinity to infinity, not just f of t times g of t, but it's also multiplied or weighted with this w function. So this is an improper integral. Please look up calculus 2 techniques for improper integrals. Sometimes they diverge. That's the problem with the whole space over the whole real line, that the integral of functions might be too big over an infinite integral. The improper integral might become infinity. So the idea is that this weight function might help actually with convergence. Very typical function for this weight function, the e to the minus t square. The negative is outside the square. Picture of this function, it's the famous bell-shaped function, used many different places in engineering, for example, and also in statistics or probability. So the idea is that this very quickly converges to zero at minus infinity and infinity, and that might help with convergence. So once we have inner product, it's an interesting question, when do we have inner product? When can we define an inner product? What spaces? If we have an inner product, then we call this vector space an inner product space. So this is the next definition. A vector space V with an inner product is called an inner product space. Many times this is written as V, and then we specify the notation for the inner product. Or sometimes we also want to specify the scalar field. Once we have an inner product, we can define the length of a vector. The length of a vector in the vector space V, if it's an inner product space, is defined using double absolute value notation. And since this is supposed to be when you take the inner product of a vector by itself, this is supposed to be a non-negative number, not a complex number, but a real number, and it's non-negative. That means we can take the square root of that. Many times this is also written as 1/2 power. This is also known as norm of a vector. Mostly we use finite dimensional vector spaces. So for example in R2, with the standard inner product or standard dot product, what we get is that if you have a vector with components x1 and x2, then when you take the dot product with by itself, you get x1 square plus x2 square, and you have to take the square root of that. And this is also called the Euclidean norm. And this is simply the length of the vector if you look at the calculation. So if you have x1 and x2 components, then the length of this vector is the square root of the sum of the squares using the Pythagorean theorem. Let me mention how often this norm is used in infinite dimensional spaces. We used continuous functions in the previous example. Integral from 0 to 1 f of t times g of t dt. And you might wonder, why do we need continuous functions for integration? We really don't need continuous functions. I mean, many discontinuous functions can be integrated. For example, the step functions, there is absolutely no problem integrating step functions over finite interval like 0, 1. We don't really need continuity. In fact, if you want to calculate norms of functions, what you get that this is the integral from 0 to 1 f square of t dt, and then you have to take the square root of that. So notice that we can have improper integral even on a finite interval, not just from minus infinity to infinity. And for example, if you consider the function f of t 1 over t to the 1/4, the graph of this function at 0, it has a vertical asymptote. At 1, the value is 1. So this function blows up as t approaches 0. But the norm of that function is not just the area under the graph. Actually, for the norm, we have to square it. So if you want to calculate the norm of this function, you get that this is the integral from 0 to 1, 1 over t to the 1/4 square dt, and then you have to take the 1/2 power. So this is the integral, the square root of the integral from 0 to 1, 1 over t to the 1/2 dt, which is actually the integral from 0 to 1, and 1 over square root of t, or actually it's better to write this as 2 to the negative 1/2. The way you integrate negative power or any power that we use the power rule for the integrals, so we add 1 to it, you get t to the 1/2 and divided by this 1/2, and you have to evaluate this at 0 and 1. It's supposed to be limit as t approaches 0, but actually after you integrate, you see that there is no problem. At 0, you can easily evaluate this, and you get that this is square root of 2. So this function has a finite norm, and this is not a continuous function on the closed interval, on the closed 0-1 interval, because it doesn't have a value at 0. It approaches infinity. So many times then, instead of, let me mention, or let me write down that 1 over t to the 1/4 function is not a continuous function, because it's not continuous at the endpoint. So then many times what we do is, instead of writing continuous functions with this norm, we just say that the L201 functions are all the functions such that their norm is finite. And then this norm, which is the square root of the integral of the square of the function, is called the L2 norm. And it's clear that all these functions, the continuous functions, are a subset of these L2 functions. There are actually many more functions in L2 space than the continuous functions. Let's go back to finite dimensional vector spaces, and let's establish some basic theorems. One theorem is that if V is an inner product space, then for any vectors uv from the vector space, and for any scalar c, the norm has the following property. So this is about the norm. If you scalar multiply a vector, then its norm gets scalar multiplied, except in case it's negative, or if it's complex, we have to take the absolute value or magnitude of that scalar. So this also explains why multiplying with a scalar means that you are making a vector longer or shorter. You are making it longer or shorter according to this norm or length property. The second property is that the norm of a vector is positive for u non-zero vectors, and this comes actually from the fourth property of the inner product. Third property is that if you have the scalar product of two vectors, so this could be, for example, a complex number, but then if you take the magnitude of that or absolute value, this becomes a non-negative number. So this scalar product, or the absolute value of the scalar product of two vectors, is less than or equal than the norms of these vectors multiplied together. This is also called the Cauchy-Schwarz inequality. And the fourth property, if you add together two vectors and then you take the norm, this is less than or equal to just adding together the norms of the two vectors. And this one has the name triangle inequality. So the first two properties are supposed to be trivial. I already mentioned that the second one comes from the inner product if you look up the definition. I'm not going to prove that part. You can check how exactly it looks. The Cauchy-Schwarz inequality, it's basically an estimation of an inner product, and this is used very often. It's used extensively. It's used in higher mathematics and even in papers. For example, I had a publication where I used it like maybe 20 times in one paper, because this might be used for so-called a priori estimates, for proving the existence of solutions. So let's prove this. First, consider the special case when the u vector is 0. So the book states in this case that it's clearly true that we have this inequality. I don't think it's completely trivial, so let me show what happens when we have u equals to 0. First of all, what we really have to see is that 0 vector times the inner product with another vector will be 0. Note that 0 times v equals to the 0 vector for all v vector. So that means that we could write, instead of the 0v inner product, we could write 0 times v inner product, and then we can factor out the 0 according to property 2 of the inner product. And I don't even care if it's the same v vector or it could be a different w vector. And the point is that no matter what this inner product is, when you multiply it with 0, you get the 0 scalar. So this holds for all v vector. And then that means that on the left-hand side we have the magnitude of 0 vector inner product with a v vector. So this is the left-hand side. And then the right-hand side, we have the length of the 0 vector multiplying the length of the v vector, but according to the second property, or actually again from maybe this second property here, if we use the 0 with inner product by itself, and then we take the square root, this will be 0. So the left-hand side and the right-hand side are both zeros. And we do have that 0 less than or equal to 0 is true, since we allow equality. So for u equals to 0, the inequality holds. Then if this is not the case, otherwise, for u vector, which is not the 0 vector, we can use the norm, which is positive, and then we can define a W vector as V minus the inner product of V with U divided by the norm of U square times the U vector. We will talk about this formula later. Right now, once we define this W vector, let's check what happens when you multiply together W and U. I will probably give this as a homework assignment, that this is actually 0. It's a simple algebra using the basic properties of inner product. And then we have that the norm of W, actually it doesn't matter what the W is, it's never negative, so the norm, especially if we square it, it becomes non-negative. And if you write this out, by definition, this is supposed to be the W vector inner product with itself. And if you substitute what the formula for W is, it's V minus V inner product U divided by U norm square U. And this is inner product by itself, so again V minus V inner product U divided by U norm square times the U vector. Also note that this is a scalar, so you are subtracting a scalar multiple of U from V. And if we use all the properties of the inner product, this is like multiplying it out like a FOIL, using a FOIL method. We will have V inner product V, then we can factor out minus the V inner product U over U norm square, and then U inner product V. So that would be this part, multiplying together with the coefficient. Then when we multiply this part with the second part of the second argument, we have a negative sign that can be brought outside. Then according to this antisymmetric property, the scalar from the second argument comes out as a conjugate, and we can do that by changing the order of the two vectors. So conjugate equals switching order. In the denominator, this is a scalar, a real number, which is positive, so that doesn't change. And then we have V U inner product in this order. And then we also have multiplying together the second terms. We have minus times minus, so that's plus. We have, so from the second component, we have from the first component of this, we have V inner product U over U norm square coming out. And then from the second component, it's the complex conjugate that comes out, which means that we have to switch U and V, the order of U and V, in order to get the complex conjugate. And again, we have the norm of U squared. And then it's U inner product with u that we have. All right, so let's try to combine like terms or do some simplification if we can. Here we have the u norm square that cancels one of these u norm squares. And then we have here plus v inner product u, u inner product v, and we have also two of these minuses as v inner product u, u inner product v, so we can cancel this with this. We are left with v inner product v, which by the way is v norm square, and then minus, here we have u inner product v, v inner product u. When we have these in opposite order, that's the complex conjugate, but then if you have two numbers like a and its complex conjugate multiplied together, this is actually the square of the magnitude. So we can use this property here and obtain that this is the square of the magnitude of the u inner product v, and this is divided by the u norm square. And we started with this 0 less than or equal to this expression. So if we rearrange it, we take this to the right hand side and multiply through with u norm square, we obtain that the magnitude square of u inner product v is less than or equal to u norm square v norm square. Looking back, what we want to show, we have this inequality with squares. Squaring things is a monotonic operation. We also obtain from here the same inequality without square. Sometimes we use an extra property that if you have a complex number, so this is a magnitude, so this proves the third property. Let me add that sometimes we also use the fact that this is a magnitude of a complex number. So for example, if we have a plus bi and its magnitude, this is square root of a squared plus b squared. And what we have that this is greater than or equal to the absolute value of a, which is the real part of a plus bi in terms of absolute value. So for this reason, and because sometimes we work with complex numbers, but we really want to only compare the real part or the imaginary part, sometimes the way we use this is that the real part of the uv inner product and its absolute value is less than or equal to the u norm times v norm. And actually the same thing is true for the imaginary part. So the real part can be used to prove actually the property 4, the triangle inequality. The definition of the norm has a square root in it, so for that reason it's easier to start with the square of the norm, because this is just the inner product of u plus v with u plus v without a square root. And then if we multiply this out like a FOIL, using a FOIL method, we get this is u inner product u, then v inner product v, then for example u inner product v, and V inner product U. These are complex conjugates. So for example, if I denote this with A, then this is A conjugate. Or even better, if I write A plus BI as a complex number, then when I change the order, instead of U inner product V, I have V inner product U. I have the complex conjugate, which means that this is A minus BI. And then when we add together a number, complex number, and its conjugate, the imaginary parts cancel out. And what I get is twice the real number. So what we have here is the U inner product U. Yeah, let me make sure that this is written correctly. This is U inner product U, which is the U norm square. Then I have, that means that now this twice the real part of UV and plus the V norm square. And then I can use this estimate of the real part, that this is less than or equal to U norm plus 2 U norm times V norm plus V norm square. And then this is, we can complete the square here to get U norm plus V norm square, the square of the sum. Comparing where we started, this is actually the inequality what we need, except this is with the square. But since the norms are non-negative numbers, if we remove the squares, the same inequality holds, the same direction, that the norm of U plus V is less than or equal to the norm of U plus the norm of V, which completes the proof of property 4. So the reason why this is called triangle inequality, because the way we add together vectors, if we have a U vector here and then we put the V vector to the position, the initial point of the V vector to the terminal point of the U vector, then this vector here is U plus V. So we have a triangle here formed by the two vectors U and V and their sum. And the length of these sides is the length of the vectors. And this is basic geometry, that the sum of two sides is always greater than or equal to the length of one side. Next topic is orthogonality. It's in the same section, section 8.1, because it's related to the inner product. So the precise definition is that we call two vectors, U and V, are orthogonal if their inner product is 0. And we had some notation from geometry for orthogonality, so we use the same notation here, even for abstract vector spaces. Although it's a question, what does it mean to have orthogonality of functions? How can you have two functions orthogonal to each other? We will look at that problem in a minute. We have additional definition saying that a set of vectors, a set S of vectors in V is called an orthogonal set if each pair of distinct vectors in S are orthogonal to each other. So we would write it the following way, that for all U, V from S, U not equal to V implies that U is orthogonal to V. We also use many times the definition of orthonormal set. Actually, let me just write orthonormal vectors. That means orthogonal with length 1. So normal usually means length 1. Example, for example in R3, we have the E1 vector, which is 1, 0, 0, the standard unit vector, E2, 0, 1, 0, E3 vector, 0, 0, 1. And it's easy to check that E1 dot product with E2 is 1 times 0 plus 0 times 1 plus 0 times 0, which is 0. So that means E1 is orthogonal to E2. And also similarly, E2 is orthogonal to E3, and E3 is orthogonal to E1. And actually orthonormal. They are orthonormal because their length is 1. So they form an orthonormal set. Another example, if we look at, for example, the sine of x and the cosine of x functions and their set, and we put them together on the interval 0 to 2 pi, with regular inner product of the integral. So if we take the inner product of sine of x with cosine of x, integral from 0 to 2 pi, sine of x, cosine of x, dx. Okay, we have to bring back some calculus 2 integration technique. So this is, by the way, using the trigonometric formulas. If we write 2 sine of x, cosine of x. Yeah, there are actually different ways to solve this. And then divided by 2. Then this is the double angle formula. So this is the integral from 0 to 2 pi, and 1/2 can be factored out. And then 2 times sine x cosine x is sine 2x dx. And now we can integrate this. The integral of sine is minus cosine. And because we have the 2x there, a little quick substitution would give us 1/2, and evaluated at 0 and 2 pi. So we get minus 1/4 cosine 4 pi, and then minus minus, so plus 1/4 cosine 0. And since cosine 4 pi is 1 and cosine 0 is 1, we get 0 here, which means sine and cosine are orthogonal with this inner product on this interval. If you want to check the normality, taking, for example, the inner product of sine of x with sine of x, in order to calculate the norm, or in this case the norm square. So this would be the integral from 0 to 2 pi sine square of x dx. Again, calculus 2, how do we integrate sine square? So this can be now integrated using the half angle double angle formula. So this is 1 minus cosine of 2x that we have to integrate, divided by 2. And then we can integrate this term by term to get 1/2 x. And the integral of cosine is sine, so we get minus sine 2x divided by 4, evaluated at 0 and 2 pi, will give us here pi. And then the sine at sine at 4 pi and sine at 0, these are all zeros. So we get pi, which means this is not orthonormal. But then what you could do is, instead of sine of x, consider 1 over square root of pi sine of x, and 1 over square root of pi cosine of x, and what we get now is a orthonormal set, because when you integrate you get a cancellation of the pi. So it's interesting to think about what orthogonality means, especially if we have functions. How can we see what it means to have two functions that are orthogonal to each other? The next theorem is the one that explains perhaps the best. It connects orthogonality to linear independence. It says that an orthonormal set of non-zero vectors, or orthogonal set of non-zero vectors, is linearly independent. So the linear independence proofs are really pretty much all the same. We assume what if they have a linear combination that's zero. So we have that, suppose we have a set of distinct vectors v1, vm that are orthogonal and non-zero. And let's see what if we have a linear combination 0. So that means c1 times v1 plus c2 times v2 all the way up to cm times vm. So how can we get a zero linear combination? So let's denote this with w, and let's take the inner product of w, which is the sum, with each of these vk vectors for any k. So what we have is that this is the sum going from 1 to m, c, j, vj with vk. We have linearity of the inner product, so we can do it term by term from the first component, and also we can factor out the cj multipliers to get then vj inner product vk. And this is always 0 except when j equals to k, since this is an orthogonal set. So what we get is that all the terms are 0 except the kth one. We get ck times the inner product vk with vk. And we started assuming that this is 0, and what we got that here this is not 0 because the vectors are non-zeros, and this is actually ck times the norm square of vk, which is positive if the vectors are non-zero. So the only way for this to be 0 is if all the ck's are 0. That means only the trivial linear combination provides 0 or can create 0. So that means that the set v1 vk is linearly independent, or the list is linearly independent. We also have a corollary to this theorem. If we compare what we had here, that this w, which is a linear combination of these independent vectors with coefficient ck, then dividing through here with the ck in this identity, we get that if w equals to the sum of ck vk, k going from 1 to n, or m, then these coefficients can be written as the inner product of w with the kth vector divided by the length square of the vk vector. So this is the coefficients of the linear combinations. There is a formula for the coefficients of the linear combination. This is also used a lot, actually, in higher mathematics in many different places. So let me mention something that's not in the book, but it's in the homework, not in our textbook. What we had here, that orthogonality for vectors, it means 90 degree. And this was the case if and only if the two vectors were giving a zero dot product. So somehow this zero dot product is related to the 90 degree. Well, it turns out that in general, if you have theta, the angle between two vectors, then the cosine of the angle is the dot product of the two vectors divided by the length of the two vectors. And because of the Cauchy-Schwarz inequality, actually this is less than or equal to 1 and greater than or equal to -1, as it's supposed to be for the cosine of an angle. The interesting thing that this holds even for functions. We can talk about not just the orthogonality of a function, which might make sense because orthogonality means linear independence. So you might expect that the orthogonality of function is related to the linear independence of functions. But now, to go a little bit more general, we also have angle between perhaps abstract vectors. So there are several more topics in this section. The next theorem is the parallelogram equality. It says that if we have two vectors u and v in a product space, then the u plus v norm square plus the u minus v norm square equals to twice the u norm square plus the v norm square. The proof of this is simple, and I will give it as a homework assignment. Just write out the two sides as inner products and then simplify and compare the two sides. So the way we introduced norm, that we used inner product for defining a norm. But when you talk about the length of a vector, initially when we start learning about vectors in, for example, the two-dimensional Euclidean space, we don't talk about inner product. We define the length of a vector using maybe a formula, and even before that, when you grow up and you start learning about the length of things, that doesn't even have a formula. It just have some kind of naive definition. So alternatively, we can start with a definition of a norm, and then we can go from there. So one possible definition is, or the usual definition is, that a norm on a vector space, and it's denoted by this double absolute value sign. So it's on a vector space. Let's use the notation U to emphasize that maybe this is not an inner product, so not necessarily inner product space, but it should be a vector space, so it should be over a field F. And it's a function, the norm is a function, where it maps from the U vector space to the non-negative integers, which is a subset of the real numbers. I'm sorry, not integers, non-negative real numbers. with the properties that, first of all, the norm of u should be 0 if and only if u equals to the 0 vector. So if something has a length, then the norm should be positive. Second property is that if you scale a vector, that means multiply with a scalar, then its length should be equal to the magnitude of a times the length of u. That should be true for all scalar a and all u vector from the u vector space. And then the third property, interestingly, we need that also, is that the triangle inequality should hold. So u plus v norm should be less than or equal to u norm plus v norm. Again, this is the triangle inequality. So now we have two definitions for a norm. One using the inner product, and another doesn't use inner product. The interesting thing is to figure out, if we start without an inner product, does it mean that this is the same norm that would come out from an inner product? It turns out that it doesn't always hold, that all norms should be coming from an inner product. There are some conditions. Actually, there is one condition. So the theorem says that for a norm on a vector space U, there is an inner product denoted by this bracket notation on U, such that the norm of U is the square root of U inner product U. That means the norm is generated by the inner product. So this holds for all U vector if and only if the norm satisfies the parallelogram inequality. Yeah, let me remind what the parallelogram inequality was. So the parallelogram inequality comes from the fact that if you have two vectors u and then another vector v, you can shift these vectors to form a parallelogram. So v parallel with each other, u shifted parallel to each other, and then one diagonal is u plus v, and the other diagonal is u minus v, according to the definition of vector addition and subtraction using geometry. The proof of this very interesting theorem that says that not all norms necessarily are generated by inner product. We need the parallelogram inequality for that to be true. The proof is not that difficult, but it's very long, so I'm not going to cover that. I'm not going to go through this. I ask that you read it. Some part is like half a page, very simple calculation with a lot of norms and inner products, tedious calculations. And some part even uses limit procedure to go from rational numbers to all real numbers. There are some examples of norms that we should look at. We looked at the two norm already. So right now we are working with n-dimensional vector spaces. X will be, it's easier to write it as a row vector, but if we usually use column vector, then we just transpose the row vector. Let's say that this is in an n-dimensional vector space V. So the Euclidean norm, or the two norm, is when we add up, this is supposed to be on the scalar field, over the scalar field, so n vectors of the scalar field. So this case, then it makes sense to use just the magnitude of the components. And we square them, and we add them up from 1 to n, and then we take the square root. So this is called the 2 norm, and it's also the Euclidean norm. Once we have this, then we can have a lot of different norms. We can have actually so-called p norms, where all we do is we replace the 2 with the p. So the p power and the 1 over p power. So in general, this is called p norm. And theoretically, p could be positive real numbers. But then some special cases, the 1 norm. So the 1 norm comes out as a special case of this, because when you take the first power, that's just the absolute value of xi, and then 1 over 1 is 1, so all you get is x1 plus x2 magnitude or absolute value added together, all the way up to xn. What's interesting is that if p goes to infinity, we get the so-called infinity norm. Xi raised to the infinity and 1 over infinity doesn't make sense as a number, but as a procedure we end up with the maximum of x1, x2 and all these components with absolute value. Then the question is, which one of these is generated with an inner product? We already know actually that the 2 norm is generated by the inner product, the standard inner product. We have seen this as an example. If you want to check whether the 1 norm is generated by the inner product or not, or a inner product, and also this is called the maximum norm or infinity norm, then we have to check the parallelogram equality. So we have to check that u plus v, 1 norm square, plus u minus v, 1 norm square. Yeah, and it's a parallelogram identity actually. So the book uses, I think, equality, and then I mistyped it as inequality. It should be really the parallelogram identity. So we want to compare this to 2 times the u1 norm square plus the v1 norm square. The question is whether it's true or not. Well, if it's not true, then it should be easy to find, hopefully, a counterexample. So we can look at this in R2, and maybe let's choose the standard unit vectors E1 and E2 for u and v, which is then 1, 0, and this is 0, 1. All right, so then the 1 norm is just adding together the components with absolute value. So the E1 plus E2, 1 norm square, is adding together the components with absolute value. 1 plus 1 is 2. Then the difference, E1 minus E2, is, oh yeah, we also have to square it. So we get 4 actually here. So E1 minus E2 is 1 minus 1 vectors, 1 norm. We have to take the absolute value, so we get again 1 plus 1 square, which is 4. That means the left-hand side of the parallelogram identity is 4 plus 4, which is 8. And if you compare this to the right-hand side, twice E1 norm square plus E2 norm 1 square. So it's 1, 0 norm square plus 0, 1 norm 1 square. But this is 1 plus 0, so it's 1. So this is 2 times 1 plus 1, which is 4. And what we have is that 8 is different from 4. So the parallelogram identity doesn't hold for the 1 norm. The 1 norm cannot be generated by inner product. since the program identity doesn't hold. For the infinity norm, which is the maximum, so we take the maximum of the absolute values. So we can check again the left-hand side of the program identity with the standard unit vectors. So this is 1, 1. Infinity norm, we have to take the absolute value and the maximum of it. So this is just 1 because it's the maximum of 1 and 1. If we subtract the two from each other, then we get 1 minus 1. Still we have to take the absolute value and then the maximum. So this is a maximum of 1 and absolute value of 1, which is 1 again. That's the left-hand side of the program identity, and if you check the right-hand side, 2 times the infinity norm square of E1 plus the infinity norm of E2. The infinity norm of 1, 0, the maximum of the components 0, 1 vectors, infinity norm. So the maximum is 1 here and 1 there, and we get 4. If we add these two together, we get 2. So again, what we have is that 2 is different from 4. The program identity doesn't hold, and that means that the maximum norm cannot be generated from inner product. Let me also note that the previous theorem actually is constructive because it tells you how to create an inner product. So constructive means that if the program identity holds for a norm, then this formula generates inner product, where the inner product is defined by the u plus v square, norm square, minus u minus v norm square divided by 4. So this is an inner product that generates the norm. Next, we need a definition for convergence. So we have a vector space with a norm, and we have a sequence of vectors, infinite sequence. We say that this sequence converges to a vector v infinity, which is also in the vector space, if the sequence vi minus v infinity in norm, as I goes from 1 to infinity, converges to 0. So what we have here is we have a sequence of vectors. It's an infinite sequence of vectors. That's something new. And for examining its convergence, we go back to another sequence, because we take the norm of these vector differences. The norm is a real number, so we have a sequence of real numbers. And again, this is infinite sequence, which we know from calculus 1 how to handle. This is also called norm convergence. It's also called strong convergence, as opposed to so-called weak convergence. So what we had before about vector spaces, pretty much we had that all finite dimensional vector spaces are just like the n vectors of the scalar field. And actually mostly we just used Rn for the scalar field. After looking at some abstract vector spaces, then we returned before, and we used the coordinate matrix to identify vector spaces with n-dimensional vector spaces to the Rn vector spaces. Now, what we're going to see is that things are even more simple than this, because it turns out that also all these norms that we looked at are pretty much the same. All this is in finite dimension, of course. So more precisely, the theorem says that the 1 norm, 2 norm, and infinity norms on Fn are all equivalent in the following sense. First of all, if we have a set of vectors converging to vector as I goes from 1 to infinity in one norm, in one of the norms, then it also converges in all three norms, so in the other norms. So these are n-dimensional vectors. So we also have that we have component-wise convergence. So, and we even have that the xi's j component converges to the x infinity vectors j component-wise for all j from 1 to n for each component. We also have that the one norm for vector can be estimated by the two norm from above if you multiply with square root of n, and then it can be further estimated by n times the infinity norm, and it can be estimated by the n times the one norm. And once we went around once, starting with the one norm, we return to the one norm, then we can actually continue this. So that means that the two norm can be estimated from below and above. Then infinity norm can be estimated from below and above with the one norm. But then it can be also estimated with the two norm. So the two norm can be estimated with the one norm, for example. Then the infinity norm can be estimated with multiples of the one norm. But then if we continue and we now substitute this inequality for x1 with the two norm, we get that this is less than or equal to n to the 3/2 two norm. And then because of this, what we have that the one norm can be also estimated with the two norm from below and from above. And also the infinity norm can be estimated from below and above with the two norm, or some multiple of the two norm. This actually also holds for all other norms, but easiest to see for these simple norms. And the proof is very simple. Again, please read this in the book. It's not complicated, and perhaps I will assign some homework assignment to check these properties. So this is section 8.1, and next 8.2 orthonormal basis.